Light can be modeled as a wave traveling through space. Some light waves have a long wavelength, while other light waves have a short wavelength. Our eyes perceive each visible wavelength of light as a different color. The range of all possible wavelengths is known as the electromagnetic spectrum. A small part of the spectrum is visible to our eyes, known as the visible spectrum. The sun emits light waves of many different wavelengths. Since they're all overlapping, we perceive the light as being white. In 1666, Isaac Newton observed that when white light passes through a triangular prism, the individual wavelengths of light become physically separated through a process called refraction. Refraction occurs in many places in nature. When sunlight shines through water droplets in the air, the refraction results in a rainbow. Another interesting phenomenon occurs if you stare directly into your phone's flashlight. Don't do this! You'll damage your eyes. But hypothetically, if you did stare into your phone's flashlight really quickly, you might see a rainbow in a circular pattern around the light. I don't exactly know why this happens, but I did have LASIK eye surgery, so that could have something to do with it. If you had multiple prisms, you could arrange them in such a way that you combine only certain colors of light. Now, I don't have multiple prisms, but I do have colored LED light bulbs. If I turn on both the red and blue light bulbs, the resulting light is a shade of pink called magenta. If I turn on both the blue and green light bulbs, the resulting light is a shade of blue called cyan. If I turn on both the red and green light bulbs, the resulting light is yellow. And if I turn on all of the light bulbs, the resulting light is white. We can take all of these results and visualize them in a circle. This is known as the color wheel. If we place white in the middle of the color wheel and interpolate all of the other colors, we can use the color wheel to predict how different colors will appear when combined. The result of mixing two colors is approximately the midpoint between them. It's important to note that the color pink is present in the color wheel, but not in the visible spectrum. That's because there's no such thing as pink light. In other words, pink is not a spectral color. We only perceive pink as a combination of red and blue light. Every color on the color wheel can be generated using red, green, and blue lights. These are known as the primary colors, and this color model is known as RGB. RGB colors are usually represented in hexadecimal form. In each hex code, the first two hex digits represent the amount of red, the next two hex digits represent the amount of green, and the last two hex digits represent the amount of blue. In hexadecimal, you count from 0 to 9, then from A to F. Therefore, the maximum value for any color component is FF. Most creative software uses hex codes to specify colors, so you should familiarize yourself with them if you're serious about your work. We can create a different color model for specifying colors based on the color wheel. The angle around the circle is known as hue, the distance from the center is known as saturation, and the amount of white versus black in the center is known as brightness. This color model is known as HSB. As brightness goes to 0, all colors converge toward black. Most creative software uses an HSB-style color picker. For example, here is the color picker from DaVinci Resolve, a video editing software. The color picker shows a slice of the HSB cone perpendicular to the brightness axis. Here's another color picker from Figma, a user interface design software. The color picker shows a slice of the HSB cone parallel to the brightness axis. The website colorpicker.dev is a helpful resource for picking colors using a variety of methods. Note that HSV is the same as HSB, except that it uses the word value instead of brightness. Colors on opposite ends of the color wheel are known as complementary colors. You may have heard that complementary colors go good together from an artistic standpoint, but this isn't entirely true. For example, if you create a gradient between two complementary colors, the midpoint goes through the gray part in the middle of the color wheel. This is known as the dead zone of the color wheel. Using the terminology of the HSB color model, the dead zone has zero saturation. There are two ways to avoid the dead zone. One way is to manually add extra stops to the gradient to force it around the color wheel. The other way is to make the gradient only affect the hue of the color and not the saturation or brightness. Most software doesn't support doing this, but it's possible to do using CSS in the web browser. I mentioned that red, green, and blue are known as the primary colors. However, you may have heard that red, blue, and yellow are the primary colors. What's up with that? When you see the color red on a piece of paper, You're actually seeing the red light that is reflected off the paper from the lights in the room. The chemicals in the red dye mostly absorb the wavelengths of light that aren't red. Adding more dyes results in more colors being absorbed instead of reflected. This process is known as subtractive color mixing. It's important to note that red, blue, and yellow are not the best choices for primary colors for subtractive color mixing. The primary colors should ideally have 120 degrees between their hues on the color wheel in order to maximize coverage. A better set of primary colors is cyan, magenta, and yellow. That's why printer ink includes these three colors. The reason you're taught red, blue, and yellow in school is that no one knows what the hell magenta and cyan are. To demonstrate how printers mix the primary colors, I have a set of color markers here. If I mix cyan and magenta, the resulting color is blue. If I mix magenta and yellow, the resulting color is red. If I mix cyan and yellow, the resulting color is green. Note that the subtractive color primaries are kind of like the inverses of the additive color primaries. As a result, we can reuse the RGB and HSB color models without needing to invent new ones. You may have noticed that there's multiple ways of obtaining the same color. For example, we can see that the electromagnetic spectrum includes the color yellow, but we can also obtain yellow by combining red and green light. Even though the components of the light are completely different, we perceive them as the same color yellow. This phenomenon is known as metamerism. Inside the eye, there are cells known as cone cells. There are three types of cone cells: short, medium, and long. Each cone cell is activated a different amount by each wavelength of light. I built this simple calculator to show how it works. It uses experimental values obtained for the typical human eye. For example, a light with wavelength 570 nanometers activates the long and medium cones by roughly the same amount. We can also achieve these same relative activations by combining two lights with wavelengths 640 nanometers and 554 nanometers. We can create a new color model based on the long, medium, and short cone cells called the LMS color model. This isn't particularly useful for digital art, but it is useful for simulating various types of color blindness. The most common type of color blindness is red-green color blindness, which can be caused by the improper functioning of either the long or medium cone cells in the eye. If the long cone cells don't work properly, it's known as protanopia. If the medium cone cells don't work properly, it's known as deuteranopia. Red-green color blindness is usually genetically linked and usually occurs in males instead of females. Complete color blindness, known as achromatopsia, is actually quite rare in humans. If we take two colors on the color wheel and combine them, the result should be the midpoint between them. Except this isn't actually true in experiments on human vision. This hints at a bigger problem with our understanding of color so far. After learning how the long, medium, and short cone cells work in the eyes, it shouldn't be surprising that nothing is simple about how color vision works. The problem here is that the concept of the color wheel is not totally accurate. If we use red, green, and blue color primaries, the only colors that interpolate as expected are within a triangle, not a circle. But then the colors along the edges of the triangle don't match the colors in the electromagnetic spectrum. This raises a simple question. How can we measure all colors visible to the human eye? Researchers in the early 1900s were also wondering how to do this, so they set up an experiment. They showed participants two colors. The color on the left-hand side of the screen was a spectral color generated using a prism. The color on the right-hand side of the screen was generated using red, green, and blue light bulbs. Participants were given 3 dials that controlled the brightness of each light bulb. Their goal was to match the color on the right side to the color on the left side. Keep in mind that light bulbs can't give off negative light, so the dials don't have negative values. But what happened if the spectral color fell outside the color triangle? This is where the trick comes in. There are also red, green, and blue light bulbs contributing to the left side. Let's say you have a saturated blue-green color on the left side. If you add red to it, the color is dragged toward white, which is inside the color triangle. Using this trick, the researchers were able to relate all spectral colors to the RGB values, even though the spectral colors themselves can't be generated using the RGB values. The result of this experiment is a picture we're going to become intimately familiar with, the CIE 1931 color space, also known as the Chromaticity Diagram. Note how there's a strange-looking edge between the red and blue colors. Remember how pink isn't a spectral color? This is the line of purples, with the shades of pink that don't fall on the spectrum. I think artists try to scientifically justify all these crazy color combination strategies, like use complementary colors or use split complementary colors. But the reality is that the color spectrum falls on this weird horseshoe shape and not a circle. The CIE 1931 Chromaticity Diagram includes X and Y axis values for all hues and saturations perceivable to the human eye. Using these X and Y values, we can define the primary colors used for computer displays. This is known as a color space. The most common color space is sRGB, or standard RGB. If you look at the metadata for image files on your computer, you can see whether the images are encoded using sRGB. Apple uses the term color profile to refer to the color space, whereas they use the term color space to refer to the color model. If you think the Apple engineers are obnoxious for doing this, you are right. Videos typically use the Rec. 709 color space, which uses the same primary colors as the sRGB color space, but handles brightness differently. The computer I'm currently using is a MacBook Pro. The MacBook Pro display uses the P3 color space, which is bigger than the sRGB color space. This allows for more saturated colors. If I take a screenshot, the resulting image file shows that it's using the P3 color space. But now we have a problem. If I take a screenshot in the P3 color space and include it in a video exported as Rec. 709 for YouTube, the colors inevitably shift. macOS includes a built-in color picker called Digital Color Meter. If you create a web page with a color like #FF0000, which is pure red, then pick the color using the Digital Color Meter, the color will not show up as #FF0000. That's because Digital Color Meter uses the Display Native Value setting by default. This means it's using the color space in the operating system's display settings, which defaults to the P3 color space. If we explicitly set Display in P3 in the Digital Color Meter, we can see what's happening. The web browser interprets #FF0000 as pure red in sRGB, but the color picker is showing the hex value for the same color in P3. Since pure red in P3 is more saturated than pure red in sRGB, the P3 equivalent of sRGB pure red is #EA3323. I bet you're extremely confused right now. I know I was when I first learned this stuff. Here's why it's so confusing. sRGB, the color space, is completely unrelated to RGB, the color model. A color space determines what colors are possible on your computer display. A color model is a way of selecting colors within a color space. To avoid confusion, you shouldn't use hex values at all to specify colors when dealing with multiple color spaces. In fact, when using CSS in the web browser, you're required to use floating point numbers instead of hex strings to specify P3 colors. The YouTuber Juxtaposed created a website called colorgamuts.com that lets you quickly test all color spaces on your computer monitor. Look at the source code in the developer tools to see the CSS used to generate each color, and use an appropriate color picker to check that the values appear as expected on your computer monitor. If you're on macOS, I highly recommend not using any third-party software when doing color-sensitive work. Use the Digital Color Meter app for picking colors, use the Preview app for viewing images, and use the QuickTime app for viewing videos. You may have heard something like the following before. Each color is given 8 bits, so the entire hexadecimal string has 24 bits. This means there are 2 to the 24th possible colors, and this means that monitors can display 16.7 million colors. This is not entirely true. The 2 to the 24th limitation is due to the fact that we're using hex strings. If we use floating point numbers for the red, green, and blue components, we can express much more than 2 to the 24th colors. The RGB color model using hexadecimal strings arbitrarily restricts how many colors can be represented. The number of bits that a computer monitor uses to represent a color is known as the bit depth. It's possible that your computer monitor has a bit depth of 8 and therefore can only represent 16.7 million colors, but this has nothing to do with hex strings. If a computer monitor is told to display a color that isn't representable with a bit depth of 8, it takes the color and rounds it to the nearest representable color. Modern Apple devices, like iPhones or MacBooks, have a bit depth of 10 bits per color channel. The benefit of a higher bit depth is that gradients are smoother and have less banding. Remember, Bit depth is completely independent of color space. Displays with higher bit depths display more colors, but those additional colors are still constrained to whatever color space you're using. Those pesky display manufacturers like to cheat when they display colors. Instead of actually using a 10-bit color depth, they use a technique called dithering to fake it. Spatial dithering is a technique that involves alternating colors on adjacent pixels. When you view the pixels from far away, the colors perceptually blend together. Certain image formats, like PNGs, can be highly compressed by using spatial dithering, but this isn't typically done by computer displays. Display manufacturers use another technique called temporal dithering. Epilepsy warning, by the way. If you have a display that refreshes at 120 Hz, your computer's graphics card can flicker between two different colors 60 times per second to perceptually blend the colors together. If the difference between the two colors is small, they'll have a low flicker fusion threshold, meaning that you won't actually see the flickering happen. In their specifications, display manufacturers refer to temporal dithering as frame rate control, or FRC. What color is white light? You might think, duh, it's white. But even children know that the sun is yellow, not white. The idea is that white is a subjective concept, and different people have different interpretations of what is considered white. The different shades of white are specified using Kelvin. 4000 Kelvin is warm light, meaning orange-ish light. 6000 Kelvin is neutral light, meaning pure white light. And 8000 Kelvin is cool light, meaning bluish light. These Kelvin values come from the temperature of a black body radiator, like the sun. Even though the sun isn't black, it's a little too complicated to explain here, but this video from the channel Physics Demos is a good starting point. I previously explained that color spaces are defined by their red, green, and blue colors in the CIE 1931 Chromaticity Diagram. But this isn't the entire truth. Color spaces must also specify the coordinates of the white point on the diagram. Different color spaces use different white points, which means color space conversions have the potential to cause a temperature shift if applied improperly. If you look at the available color spaces on a MacBook Pro display, you can see that there are several options that look similar, like P3D50 and P3D65. The D50 and D65 refer to the white points of those particular P3 color space variants. The app I use to control my color LED bulbs actually includes a slider to control the color temperature of the light. Older incandescent light bulbs tended to have a warmer color. People are so used to it by now that most regular LED bulbs are also sold with warmer colors. If you ever use professional camera software, like the Blackmagic camera app for iPhone, you'll be able to adjust the color temperature of the video that you're recording. The way we see color depends on the brightness of the color. If we look at a rainbow as displayed on a computer screen, the color yellow seems much brighter than the color blue. In fact, if you go into your computer's accessibility settings and change your display to grayscale, you'll see that yellow does indeed appear brighter than blue. Instead of simply averaging the red, green, and blue components of the colors, the operating system uses a weighted average that better reflects how humans perceive brightness. If we apply this transformation to the chromaticity diagram, we can see that it doesn't have a uniform brightness. A related problem was described in 1942 by David McAdam. He found that there's regions of the chromaticity diagram that visually appear to have the same color. These regions vary dramatically in size, which isn't desirable for something like a color picker. As you might suspect, the individual regions tend to have a uniform brightness. In 1976, researchers created the CIE Lab color space. It's designed to solve the brightness problem by being perceptually uniform. However, it has a major flaw when interpolating colors for gradients. The gradient from blue to white contains the color purple. So in 2020, Bjorn Ottoson developed the OK Lab color space. We can take the HSB color picker and replace it with a perceptually uniform version based on OK Lab. When converting to grayscale, the colors have a nearly uniform brightness. Perceptual uniformity is important if you're trying to create a color theme for your website or app. If you're using Tailwind CSS for styling your website, colors with the same number identifier, like red 300 and orange 300, will appear the same when using a grayscale display. Tailwind uses the OKLCH color model, which is based on the OK Lab color space. You can find an OKLCH color picker at oklch.com. I think there's a lot of articles about OKLab, given how recently it was created, but some of these articles make it sound like it's the second coming of Christ, so I think it's been overblown a little bit. The relationship between perceived brightness and actual brightness is not linear. If you double the physical amount of light in a room, it won't feel twice as bright to your eyes. To handle this, in addition to the color primaries and white point, color spaces must also specify a transfer function. A typical transfer function is defined in two pieces, one linear piece for colors near pure black, and one exponential piece for all other colors up to pure white. In practice, the key difference between transfer functions is the value for the exponent, usually denoted by the Greek letter gamma. When you import video footage into video editing software, like DaVinci Resolve, it's very important that the software correctly interprets the color space of the video. Otherwise, the video will appear oversaturated or undersaturated. I've seen many YouTube videos with gamma shift issues that the uploader probably never noticed. Up to this point, we've mostly been looking at color in 2 dimensions. If you look in the ColorSync utility app bundled with macOS, you can actually see the 3D representation of all the different color spaces. You can also see which transfer functions are associated with each color space. Dynamic range refers to the difference in brightness between the brightest and dimmest parts of an image. Generally speaking, cheap cameras tend to have limited dynamic range, resulting in overexposed white areas or underexposed black areas. However, some cameras have massive dynamic range. To display a high dynamic range image, you need a high dynamic range display, also known as an HDR display. Although HDR allows for accurately displaying certain types of scenes, there are some major drawbacks. Whenever I encounter an HDR image on the internet, it's extremely bright compared to the surrounding images. In fact, it's so bright that the iPhone and MacBook displays gradually increase the brightness to maximum to give your eyes time to adjust. Another problem is that HDR images aren't brighter at all on the iPhone when outside in the sunlight. The iPhone boosts the display brightness so high that there's no room left to show HDR images brighter than the regular ones. I was considering uploading this video to YouTube in HDR, but I refused to use it because I think it's stupid. For a fun demo showing how bright HDR videos can get, visit color.tastemaker.design. If you enjoyed that video, make sure you love tap that subscribe button. Shout out to Ricardo Torres Guzman for your continued support on Patreon, and I'll see you guys next week.